Hello, welcome to this video 6-6, and we are going to talk about the second fundamental theorem of calculus, which is a very important and common concept across calculus, and that's what our learning intention is to do today, is to utilize the second fundamental theorem of calculus to differentiate integrals. What? The big idea from the first semester with the big idea from the second semester? That is correct. That's what we're going to do. We're going to differentiate integrals. So, in previous sections, we have worked with functions defined by integrals like the following. So here's an example of g of x is equal to the integral from 1 to x of f of t dt. And we've encountered these problems through graphs, and we've found function values by connecting the idea with area. But now we're going to go ahead and consider the functions defined by integrals and introduce this very important concept in calculus. So we're going to go ahead and let a be a constant value for the function below, and we're going to let u be equal to some other function, just some other value. So here's a, here's u, some other function, and just to give example, a could be -1, u could be x cubed. You could substitute any simple idea in order to go ahead and do this. So here's what we want to do. Again, we want to differentiate functions defined by integrals. So if I have a function g of x and it's the integral from a to u, some function up here in your upper limit of the function f of t dt, we want to find g prime of x. So in order to do this, we are going to go ahead and we need to find here the limits. We need to use the limits in order to evaluate the definite integral. And we are just going to use our idea from the first fundamental theorem of calculus. And then what we're going to do is we're going to differentiate our answer. So we'll just break it up into pieces that we know how. Differentiate our answer. So step one, let's go ahead, let's use our first fundamental theorem of calculus in order to evaluate what g of x is. So it's the integral from a to u of f of t dt. Well, we know that the antiderivative of f, if I integrate f of t, that's going to be a capital F. And I'm going to go ahead and evaluate this from my limits, right? The upper limit, so f of u minus f of a. Now, here's the very important part here. Remember, a, this is a constant. This is a constant. So this is just a function evaluated at some number, and that's just going to be a number. It could be any number. Just think of any number in the world from negative infinity to positive infinity, okay? And that's just a constant. So here's the big idea. Well, if I go ahead and I differentiate that statement, f of u minus f of a. Remember, f of a is just a constant. It could be the number 2. Well, what happens? Well, the derivative of f of u, that's going to be a lowercase f of u. And then u, remember, is a function. So I'm going to have to multiply times u prime. Minus, so all I do is differentiate this, and you're going to have to think back to last semester, right? I take the derivative of a function, here, you know, capital derivative of capital F is lowercase f of u, and then I have to multiply times u prime, the derivative of the inside. That's chain rule. Okay, and then the derivative of a constant we know is 0. We know that this goes to 0. So, there you go. That is the second fundamental theorem of calculus, and a very big idea. If you go ahead and look at where we were, so g of x was the integral from a to u of f of t dt. How did I go to this? Well, pretty much all I did was I took u and I plugged it in. The function didn't change, right? Because I'm integrating and I'm differentiating. Well, those undo each other. And then I have to multiply times the derivative of your upper limit of that function, u prime. And this leads to a very huge idea that the derivative and the integral, these are inverse functions. Inverse functions. Foundational concept to calculus. And here is the second fundamental theorem of calculus, clearly and plainly defined. Okay? So the second fundamental theorem of calculus says if you're taking the derivative of an integral from the limits a to u, where a is a constant and u is some function of f of t dt, then that's just equal to f of u times u prime. And I also want to go ahead and jot down another format that we'll see in the homework, and I'll do one example. But if I integrate this, let's say, I'll put u up here and I'll put t down here. No, not t, because we're defining t. I'll just put, well, I'll use a and b. Sorry for my indecisiveness. A and b, and where a and b are functions. Here, a and b are functions. I should make sure that that's clearly stated. Okay, f of t dt, a and b are functions. Well then, I'm going to integrate this and differentiate. What you would end up with is f of b times b prime minus f of a times a prime. And this should make clear sense. You can see here your first example connected to the, your first limit plugged in, connected to your second fundamental theorem of calculus, and then I'm subtracting the lower limit as a function times its derivative times a prime. Oftentimes you'll see your lower limit as constants, but I just want you to be prepared in case you do see both limits defined as functions, because that is possible. All right, so some important notes. One, the second fundamental theorem of calculus is what we use when we need to differentiate a definite integral with variables in the limits. And that's important. If you have variables in the limits and you're differentiating the integral, then you use it. The second fundamental theorem of calculus allows us to differentiate a definite integral without integrating or differentiating the integrand itself. I don't have to touch the integrand, and that's beautiful, because sometimes and oftentimes these functions will be very, very nasty, very, very ugly, almost like your significant other, until you realize the beauty within, obviously. And you don't want to touch that. You don't want to differentiate or integrate that function. Well, it's beautiful because the definite integral and your derivative are inverses. They cancel each other out. So since we're ultimately taking a derivative, we will use the chain rule and multiply times the derivative of u. That is the limit of the integral. Okay, so let's go ahead and look at some basic concepts here of how you will see them on the AP exam, generally on the multiple choice section. Example 1, find f prime of x for the following. Okay, and we're defining f prime of x is equal to the integral from 0 to x of cosine of t squared dt. Now this is as foundational as it gets, and I'm just going to write it right underneath f prime of x. I'm taking the derivative of the left. I'm going to take the derivative of the right side. Well, that's the derivative of an integral. So remember, the derivative and the integral, they cancel each other out. So all I'm going to do is I'm going to plug in my limit. I have cosine of x squared, and I'm going to multiply times the derivative of x, which in this case is 1. Now, you don't have to write this, but I'm going to write that just until you get this idea solidified. That's it. B, f of x equals the integral from -1 to 3x of e to the power of 2t dt. Okay, so I'm going to go ahead and I'm going to differentiate my left side, and I'll differentiate my right side. Well, I'm taking the derivative of an integral. They're inverses. They cancel. But I have a function up here, so I'm going to go ahead and I'm going to plug in my function, e to the power of 2 times 3x. That's a 2. Almost looks like a letter there. Okay, and I'm going to multiply times the derivative of my upper limit, which is just 3. Okay, and I'll clean this up. Again, of course, multiple choice, or if this was free response, you don't have to, but you'll probably see this represented as 3e to the power of 6x. C, f of x equals the integral from 1 to the power of x squared of the natural log of 3t minus 1. Absolute value of 3t minus 1 dt. Now, they're going to start to scare you. These functions are going to start to get really ugly, and you're going to freak out. You're like, I don't know how to integrate that. I don't know how to differentiate that. I'm scared. Well, don't be. You're taking the derivative of the left side. You're taking the derivative of the right side. Well, Derivative of an integral, they cancel. But I do have to do something with this limit. I'm just going to plug it in. The natural log of the absolute value of 3 times x squared minus 1. Okay, and I have to multiply this now times the derivative of my upper limit, times 2x. Ta-da! There it is. There it is. Okay, and D. I'm going to go ahead, ooh, well, this one has a curveball. This one has a curveball. Pause the video, try this one, see if you can catch the curveball or the trap, and then I'm going to go ahead and I'll show you that and allow you another chance to practice this one. But try D real quickly. Okay, here is D. What I'm going to go ahead and do is I'm going to, what you should notice is that constant value is in your upper limit, and you want that in your lower limit. So what I'm going to do is I'm going to redefine this integral as the negative integral from 5 to 2x square root of 4t minus 1 dt. Okay, so don't be scared again when something looks weird. Remember that property. I can go ahead and I can flip my limits and then add a negative, and we're in business. Okay, so go ahead, pause the video if you haven't, if you didn't catch that. Now try it. I'll show you the answer here in a second. All right, so here's the solution. Again, I'm taking the derivative. F prime of x is equal to negative, well, the derivative of the integral. I'm just going to go ahead and plug in my function. 4 times 2x minus 1, okay, times 2. That's the derivative of your upper limit. And you get negative 2 square root of 8x minus 1. And there it is, your f prime. Pretty easy, right? All right, here is example number 2. Let's go ahead and look at these ones. Now, notice I don't have a function defined as another function. They're just flat out saying, what is the derivative of the integral? And in your mind, you should be thinking, hey, these cancel each other out. Okay, but I have to do something with this. It's not like everything just disappears. Okay, I have to go ahead and plug in that limit. So this is equal to tan of 2 times x cubed times the derivative of the upper limit, which is 3x squared. And there you have it. Now you may see that 3x squared come out in the front, but that's it. That's all there is to this. B, the derivative with respect to x of the integral from 0 to 2x minus 1. Of 2 over 5 minus 6t dt. Okay, well, they're integral, or a derivative and an integral, they're inverses, they cancel each other out. So I have 5 minus 6 times 2x minus 1, and I'm going to multiply times the derivative of the numerator, which is 2. So if I was cleaning this up, a multiple choice, I'm going to assume they want me to go ahead and clean this up. 5 minus 12x plus 6, we could combine that 5 and 6 to make 11. So 4 over 11 minus 12x. Pretty simple, right? Pretty simple. Okay, C, go ahead, pause, try this one. Let's see if you remember good old e to the x. All right, hopefully you tried this one. Derivative and integral, the second fundamental theorem of calculus, they cancel each other out. They're inverses. So this is just the square root of 2e to the x minus 1 times the derivative of the upper limit. That's still a function e to the x, and derivative of e to the x is e to the x. All right, you got it. Good job. Okay, D. Do you want to go ahead and try this one now? Ooh. We got a trick, we got some trig. I think you're up to the task. You got this. Pause me, check your work. All right, here I have a derivative of an integral, and what I notice, those are going to cancel each other out, but notice my function's not in the numerator. So what I am going to do is I'm going to rewrite this, or at least include this in my answer, is I'm going to flip my limits of integration. So that sine of 2x, that function is in the numerator of e to the power of t squared dt. Okay, so what I get is negative. Derivatives and integrals cancel, and I have e to the power of sine of 2x squared. All of that is squared. okay? And then times the derivative of my limit. Well, I have a trig derivative of sine. If you forgot, here's a good time to reintroduce. Remember, this is where cosine of x is 1. Here's where sine of x is 1. This is where negative sine of x is 1, negative cosine. And remember, derivatives just follow this pattern. Derivative sines cosine, derivative cosines negative sine. And it just follows this wonderful circle of life. So anyway, times cosine of 2x, don't forget the chain, which is 2. We have a 2 there, okay? And we could go ahead and clean this up. We could clean this up. So we get negative 2 cosine of 2x times e to the power of sine squared 2x. There you go. All right. Here is an actual AP exam from the practice, or a question from the practice exam, the 2009 number 27, and it says, if f is the function given by f of x equals the integral from 4 to 2x of the square root of t squared minus t dt, then what is f prime of 2? Okay, well, in order to get f prime of 2, you know what I need is I need f prime of x first, and I'm taking the derivative of an integral. Oh, hey, it's like we were just talking about this. I'm going to go ahead, I'm going to plug in my limit, so 2x, that whole 2x gets squared. So make sure you use those parentheses wisely, right? You're squaring the whole thing. Okay, so 2x squared minus 2x times the derivative of 2x, which is a 2. So let me clean this up just before I evaluate this. This is 2 times 4x squared minus 2x. Okay, there's f prime. And what I want is I want f prime of 2. So I'm going to plug in 2. 2 times the square root of 4 times 2 squared minus 2 times 2. That's lots of 2's. We got 4 times 4, 16 minus 4. It's the square root of 12. 2 root 12. I got e. What do you guys got? Do you got that? I'm surprised they didn't break this down. I'm surprised they didn't pull out the, square root of 4, make it what? 2 times 2 root 3. I honestly would expect that. 4 root 3 to be the answer. But hey, calculus. I guess they don't care about your algebraic skills. All right. Here is a practice example, 2013. Go ahead, pause this. Try this example. Let's see what you got one last time before we go ahead and look at applications of the second fundamental theorem of calculus. Okay, for this one, they give a little bit of domain. They say for x is greater than 0. That's just because the argument of a natural logarithm, the domain has to be bigger than 0. Can't be 0, cannot be negative. Logarithms, look something like this. They have an asymptote. Remember, they're the inverse of an exponential. So logarithms, it's not letting me grab. Hold on, technical difficulties. Okay, I think we're back. Let's see if it lets me graph this time. All right, it does. Okay. So this is what a logarithm looks like, more or less, where right here, that 0 is 1 comma 0. So anyway, pretty much it doesn't matter. It's what I was trying to get at. I'm taking the derivative of an integral, so this should have given us natural log of 2x. That whole 2x is cubed. More than likely, that's what is probably going to shoot you guys in the foot. And I multiply it by 2, so this should be 2 natural log of 8x cubed, 2x times 2x times 2x. Okay, a lot of times students will just apply the 3 to the x. So your algebra skills totally matter for this one. You should have gotten D. All right, here is where the fun begins. Where's that meme of Anakin Skywalker? I don't know if you guys even know who Anakin Skywalker is. You guys probably know who Rey, quote unquote, Skywalker is. She's not even a Skywalker. She's actually a Palpatine. Anyway, I digress. So let's go ahead and let's tie back to Unit 5, your guys' favorite unit, where I asked you questions like, hey, where's the function increasing? Where's the function decreasing? Where is it concave up? Where is it concave down? And you had to justify, yes, I'm going to marry these two wonderful ideas. So we have here example number 3, and it says let f of x be defined as the integral from 1 to x of this beautiful integrand 2t cubed minus 3t squared minus 12t plus 7 dt. And they want to find the intervals where y equals f of x is concave up. A lot of people are going to look at that function defined by an integral and freak out. What you need to do first is you need to interpret the question first. Like, ignore what they give you. Ignore the prompt, ignore the information. I mean, you know, a little bit. How do I find where a function is concave up? And what your brain should say is, hey, this is where the second derivative is greater than 0. I need the second derivative greater than 0. Okay, well, then go ahead and do that. Find the first derivative and then find the second derivative and just do the analysis. It's not that hard. Okay, let's go ahead and do that. So first, I know you're like, Sharper, you've been teaching calculus for X number of years. You're a mathematician. No, it's simple. You got this. Calculus is just scary in the name. So f prime of x. Hey, I need the derivative of an integral. Derivative of an integral? Hey, they're inverses. They just cancel. All I do is I just plug in the variable and the limit. Isn't this so easy? Oh my gosh, like stealing candy from the proverbial baby. All right, there's f prime. Okay, class. Now, how do I find f double prime? Take the derivative again. Well done. F double prime of x. This is equal to 8x squared. Ooh, brush up on that power rule, man. Derivative of 3x squared is going to be negative 6x. Don't forget to drop your powers by 1. Sometimes that's where you get a little bit of a rusty. See, and I can't even multiply 2 and 3. 2 and 3. That's 6. Okay. So there's my function. I want to find where is this function greater than 0. So what I'm going to do first is I'm going to set it equal to 0. I'm going to solve this. This is 6. I'm going to factor out a GCF, make this much smaller, and all of a sudden I have a quadratic equation that I need to factor and solve. Okay, so this looks like x minus 2x plus 1. And it looks like, if I were to draw an f double prime number line, it's going to be equal to 0 at x equals 2 and x equals negative 1. So here's negative 1. Here is 2. Okay, so where is it bigger than 0? Where is f double prime bigger than 0? Well, look at your f double prime function, which I'm just going to look at this form, and that's just a parabola. Isn't that an open-facing parabola? Right? I don't have a negative anywhere to flip it. It's going to look something like this. Okay, so I know f double prime is positive on this interval, positive on that interval. There you go. That is it. So, okay, let's go ahead and answer the question. And then they say justify, I would say. Well, they don't even say justify, but we're going to go ahead and do it anyway. So we can say f of x is concave up on negative infinity to negative 1, union 2 to infinity, because f double prime of x is greater than 0. Boop! There you go. There you go. You'll definitely want to show your work. I think it's important to show the transition from here to here to here, right? Remember, assume the reader knows nothing and everything all at the same time. Okay, before I let you go, we are going to go ahead and look at an actual FRQ response. Here we have 2014 AB3, and this is a graphical response. Here's the graph of f. And they say the function of f is defined on the closed interval negative 5 to 4. The graph f consists of 3 line segments and is shown in the figure above. Let g be the function defined by g of x equals the integral from negative 3 to x of f of t dt. Okay, so they define g, and notice that g is the integral of f. That's very, very important that you tie this together, right? So I'll go ahead and I'll talk about how to label this graph here in a second. But they say find g of 3. And I'm not going to overreact. I'll take the information as it comes. Find g of 3. Okay, well, g, right, g is given right here. So all I'm going to do is I'm just going to evaluate this function. So g of 3, I'm going to plug it in. I have the integral from -3 to 3 of f of t dt. Now, how do I find that? Well, that's just the area under the curve. I have f here. Okay, here is -3. Here is +3. And I'm going to go ahead and I'm going to calculate this area. So that's going to be this triangle. That's simple. 1/2 times the base, -3 to 2, that's 5, times the height, 1, 2, 3, 4. Okay, found that one. Plus this area, which actually isn't going to be a plus. Well, I'll let the height take care of it. 1/2 times the base, which is 1, times the width, or sorry, the width, which is 1, times the height, which is a -2. Okay, you can eyeball it. You can see that. Also, too, analysis of the slope will tell you that that is -2. So, looking at these values, we go ahead. We get 10 minus 1. Remember, that area should be negative because it's below. We get 9. B. On what open intervals contained in -5 less than x less than 4 is the graph of g both increasing and concave down? Give a reason for your answer. Where is g increasing? Well, I know g is increasing when g prime is greater than or equal to 0, and then concave down when g double prime is less than 0. So I need to find these two areas, and I need to figure this out. Now, first, I don't have g prime. I don't have it defined. You'll want to do this. So I'm going to go ahead right off to the side. I'm going to make sure I say, okay, g prime of x is equal to, and notice what we're doing. I'm taking the derivative of an integral. Well, second fundamental theorem of calculus, they're inverses, they cancel, and the lower limit, which is a constant, disappears. So g prime of x is equal to f of x. Now, when this comes up, when they say, hey, f of x is g prime of x, I like to go up here and I like to say, hey, what you're looking at is g prime of x. That graph is also g prime of x. So right away, I can look at this graph and I can say, all right, where is it greater than or equal to 0? Well, all of this region, okay? G prime is bigger than 0, here bigger than 0, and then here equal to 0 finally, right, at these 2 points. Okay, so on those intervals, all right, I got that. And then I need to define where is g double prime, well, or what is g double prime of x? Well, that's just f prime of x, f prime of x. That's the slope. And I want the slope to be less than 0. I want it to be negative. So where is this happening? Where are we above and slope is negative? Here and here. Notice they said the open interval, So I will say, well, I'll just have to zoom in and out. You're going to have to live with me. I'm sorry if you've made it this far. G is both increasing and concave down on -5, what was it, -3? Oh yeah, hey. I have a eidetic memory, so that's why I seem super smart all the time. You guys are like, yeah, right. You test us way too much. 0 to 2. 0 to 2. 0 to 2. Hey, I answered the question. They also say give a reason. Whenever you do this, whenever you give this analysis, prepare to give a reason. How did I know? How did I know this? Well, is what your brain did to come up with this answer. Where is g prime greater than or equal to 0? And where is g double prime of x less than 0. And I'm going to say because BC G prime, which is equal to F, is greater than or equal to 0, and G double prime, which is equal to F prime, is less than 0. There you go. I know you're going to ask me about, hey, do we have to put the F? I mean, I already put G. I like the G. I also like the F because that's what's given up here. You're using that graph of F. I don't like F by itself. I definitely want to use G. But we'll look and talk more about this when we get to AP exam review at the end. Okay, C. Last question. I'm going to go quick. Here is just a blast from the past, a derivative question. The function h is defined by h of x, which is g of x over 5x. Find h prime of 3. All right, AP exam is going to test you on your derivative analysis. This is just quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top, all over, don't forget, all over the whole denominator squared. Okay, so there's that, and they want h prime of 3. H prime of 3. Okay, so we have 5 times 3, that's 15, times g prime of 3. I'm going to have to go to the graph for that, or my function. 5 times g of 3. Oh man, this one's going to be a little bit harder. And this is just 25x squared. So 25 times 3 squared, which is 9. Okay, and I need g prime of 3. Sometimes they'll be nice. They'll give you these values from before. So g prime of 3. Remember, g prime, whew, that's the same thing as f of x. So what's f of 3? F of 3, right here. Boop, we said -2. Okay. Is it -2? It is -2. G prime of 3. Okay. I don't know why I'm scared of this answer. I feel like I made a mistake. Minus 5 times g of 3. What's g of 3? Well, lo and behold, what the heck did we do in part A? Wah, 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 wah. They love to recycle answers. So, if you screw this up, if you had no clue in this section and you came up with a non-zero answer, just live with it. Just plug in what you got, and then they're gonna use that as a correct answer for part whatever this is. This is C. Okay, so 25 we got times 9. Okay, if you're neurotic and you really want the answer, go for it. I'm not going to box it. Don't box answers on the AP test. Okay, there is my h double prime of 3. We're at 32 minutes. Man, this was a monster of a lesson, but we talked about a huge, huge idea. The second fundamental theorem of calculus. Here it is. Take a picture, sleep with it, dream about it. Catch you in the next video. Like and subscribe. See you next time.